So in this next section of notes, we're going to talk about the two different types of circuits that we're going to analyze. And then the only thing beyond this is actually analyzing them and learning some of the stuff about that. But we're going to talk about series circuits and parallel circuits. And these are the two main types of circuits. Series circuits just means that there's only one path for current to follow. And a parallel circuit will mean that there's going to be a branch where current can split up. So that's what we're going to be talking about in this section. So we're going to go ahead and start with the concept of series circuits. So series and parallel circuits, if I have two light bulbs, so in each of these circuits below, I have two light bulbs. Now, how I wire those light bulbs will have very different effects on the light bulb itself. So on the one on the left, we'll call this circuit 1. These two light bulbs are in one path, in the same path as each other. So this is called connected in series. In series means that there's no junctions, there's just one path. Now, a note about this is that old-style Christmas tree lights used to be connected in this way. So why is this a bad idea, thinking back to the concept of continuous conducting path? Well, if one of these light bulbs burns out, then it creates an opening in this circuit where current cannot flow through, which means that, let's say instead of two light bulbs, I had 30 light bulbs. If a single light bulb was burnt out, the whole circuit goes out. So you have to sit there and troubleshoot and figure out which light bulb isn't working that's causing the whole circuit not to work. Now, new style light bulbs are measured in the second circuit, which is the parallel circuit. So the parallel circuit means that there's a branch. The current can either go this way or it can go this way. And if one light bulb goes out, it's fine. The rest of the circuit will still work. So why not do it this way? Well, it requires more wires. So it's cheaper to make the series circuit than it is to make the parallel circuit. So let's keep diving into this concept of a series circuit. Now, if I have resistors in series, we know that according to Kirchhoff's loop law, the voltage drop across the entire circuit has to equal 0. So we get electric potential energy, or we get voltage from the battery, and then each of the resistors drops some of the voltage. Since there is no junction, the current has to be the same through each of the resistors. So we can use Kirchhoff's loop law to look at the potential differences. And we know that if this is, let's say that these two resistors are identical. Let's say this is a 6-volt battery. Each resistor will get 3 volts because they have the same current, and we're assuming right now that they have the same resistance. So the current, key concept, the current is the same throughout a series circuit. So the voltage drops, I can use this concept of the voltage drops and Ohm's law to solve for what that current must be. And in this case, the current is the battery, the voltage of the battery divided by the sum of the resistors. So R1 plus R2. So I got a quick check here. I got a 12-volt battery, a 12 ohm, and a 6 ohm resistor. So in series, the resistances actually add together. We're going to talk more about that. So the equivalent resistance is going to be 18 ohms. Well, 18 ohms, and I got 12 volts. So 12 volts divided by 18 ohms is going to be 0.67 amps. So that is the current throughout that entire circuit. It's 2/3 of an amp. All right, now let's look at this one. This one's a little bit more confusing. Imagine now, if I look at Kirchhoff's loop law, I start at 0 right here. I'm gaining 4.5 volts, and then I'm gaining another 3 volts. So at this point, my electric potential energy, or my voltage, is 7.5 volts. I lose 3 volts right here, so now my electric potential is 4.5 volts. This is a question. The next one is a question mark, and then I lose 2.5 volts, which means that I would have 2.5 volts dropped right here. So in order for it to get back to 0, I have to drop 2 volts across this 200 ohm resistor. So Kirchhoff's loop law helps us a lot when talking about this series circuit. So series resistors, let's talk about resistors first. The concept of series resistors are actually very simple. If I had two resistors and I wanted to replace them with one, and the concept of equivalent resistance and equivalent resistors means that if I take the resistors and I replace them with other resistors, but the battery does not know the difference. In a series circuit, my equivalent resistor is just the sum of the two individual resistors. So if I had, for example, that was wonderful, a 3 ohm resistor and a 6 ohm resistor. In a series circuit, I could take that out and instead put in a 9 ohm resistor, and this battery doesn't know the difference. It's going to operate exactly the same, and most importantly, the current is exactly the same. So that's what an equivalent resistor is. And in a series circuit, it's just the sum of each of the resistors. So here's our formula for it. If I could have 100 resistors, it doesn't matter. The sum of all of the resistors is going to equal my equivalent resistance. Now, the reason that this is important is as we're trying to analyze circuits, if I get a complex circuit, which means it has a lot of stuff going on, I can draw what I call equivalent resistance circuits, which means that it's exactly the same, but I can simplify that circuit to make it easier and easier and easier so that I can analyze it later on. And we will definitely be doing that a ton towards the end of this unit when we talk about complex circuits in section 23.5. So the equivalent resistance in a series circuit is the sum of all of the resistors. So that's it for series circuits. Now let's jump into parallel circuits. And again, with parallel circuits, before I had my light bulb 1 and light bulb 2, and now I have light bulb 1 and light bulb 2. And it's so similar, but it's different. And the reason that it's different is because I have this branch right here where current can go in either direction. So we have to learn what exactly does that do to the concept of how this circuit is working. So here's my picture again. The main concept with parallel circuits, I have two resistors in parallel. I can trace a path back. So there's one. I'll do the other one a different color. And there's two. Each one, I could argue, are directly connected to the battery. Okay, so each of these resistors is directly connected to the battery, which means that, in this case, that the voltage drop, either V1 right here or V2 right here, in each of these cases then, the voltage drop has to be the same as the battery. So before, let me go back to my series circuit concept. I'll draw it right off to the side here. If I have a 6-volt battery, each of my resistors, or each of my light bulbs, are each going to get 3 volts, because that satisfies Kirchhoff's loop law. 6 volts in, 3 volts and 3 volts, 6 volts out. Well, with this one, let's say that this is a 6-volt battery. Since they are both connected directly to the battery, R1 is going to get 6 volts, and R2 is also going to get 6 volts. And this is kind of confusing because you might say, well, doesn't this violate Kirchhoff's loop law? And actually, it doesn't. It actually says that it's correct. So if I start at, let's say I'm starting at the battery. No, let's start right here. All right, 0 volts, 6 volts in, 6 volts out, and I'm back to 0. Okay, let's start here again. 6 volts in, 6 volts out, and I'm back to 0. So each one of the resistors are technically hooked directly up to the battery, which means that they get the full voltage of the battery. So even though it's 6 volts in, 6 volts out, 6 volts out, it doesn't violate this concept of the conservation of charge. They're both getting 6 volts. So something else has to be going on. And what has to be going on actually brings us back to the concept of Kirchhoff's junction law. So there's a current coming out of the battery. Some of that current goes here into I1. Some of it goes here into I2. And the total current, according to the junction law, the total current of the battery equals the sum of each of those two individual currents. And then I can use Ohm's law to find the current coming out of the battery based on the two resistors. And we'll talk about that more in just a minute. So what is actually happening is the current is splitting to provide the same voltage equal to the EMF in each one of the branches. So what's actually happening is when I have a parallel circuit like this, it's not that the battery puts out more voltage. The battery actually has to push out more current. So the current in this situation, in the parallel circuits, coming out of the battery is more than the current in the series situation. How the battery knows to do that, I don't know, but it pushes out more and more current. So if I have two batteries hooked up in series, two light bulbs hooked up in series, it's using less current from the battery than the two light bulbs hooked up in parallel. And in class, I set these circuits up and we can really take a look at it and really analyze and see what's going on in each of these circuits. So, similar to before, I want a formula for my equivalent resistance. And in the last slide, I kind of set that up. Well, here's the finished product. The equivalent resistance of a parallel circuit, meaning that if I were to replace all my resistors with one resistor, I take the sum of each of the resistors, I take the inverse of each of the resistors, I add them all together, and I take the inverse of those inverses. A little confusing, right? But let's say I have two 2-ohm resistors, right, in parallel. My equivalent resistance is going to be 1 over 2 ohms plus 1 over 2 ohms to the -1 power. So 1 half plus a half is 1. The inverse, the -1 of 1, is going to be 1 ohm. So if I have two 2-ohm resistors in parallel, I could replace them with one 1-ohm resistor, and the battery would not know the difference, and it would get the same current. Which means that the equivalent resistance in a parallel circuit is always going to be less than the smallest resistor in a parallel circuit. Kind of confusing, but the more resistors I add in parallel, the less equivalent resistance it gets. And that pushes out then more current from the battery. All right, so here again, if we're taking a look at a quick little example, here's one battery, same battery, identical batteries. One light bulb and one light bulb here, which means it's getting, let's say it's a 6-volt battery, it's getting all 6 volts. So if this is still a 6-volt battery, how do the brightnesses of B and C compare? Well, they're going to have identical brightnesses to that battery, or to the light bulb A, because they're each connected to the EMF, which means that all of it's going to get 6 volts. So what has to happen is that the battery has to increase the amount of current that it pushes out to make that happen. More light bulbs, more resistance, but because they're in parallel, the equivalent resistance is less, which makes the current become more, as it has to branch into each of the two branches. All right, so I got a quick check here. Which resistor dissipates more power? Well, they're both getting 9 volts, but we had a bunch of different formulas for power, and one of the formulas was V squared over R. So the less the resistance, the more power it gets. And here's another reason why. As the current is coming off the battery, it's going to split into these two branches. And current tends to follow the path of least resistance. And that's like a law of nature. So current is going to flow a lot to this 1 ohm resistor because it's the least resistance. So more current is going to lead to more power. All right, so here's an example. I have 3 resistors right here. They're all connected to a 12-volt battery. Boom. And my question is, what's the current provided by the battery? And the answer is there's multiple ways to actually figure this out. So what do I all know? Well, I know that since they're all in parallel, they all get the full 12 volts. I'm actually going to solve this problem 2 ways. And I know, since I know they all get 12 volts, I can use Ohm's law, and I can say that the current in each branch equals the voltage divided by the resistance. So if I were to say, all right, in branch number 1 here, I have 12 volts and I have 58 ohms. So I do 12 volts divided by 58 ohms. I get 0.206 amps. All right, what about the second branch? I have 12 volts divided by 70 ohms. And here I get 0.171 amps. Now, there's going to be some errors here because I got some round-off errors because these are not perfect fractions, but that's totally fine. 12 divided by 42, 12 volts divided by 42 ohms, I get 0.286 amps. Okay? So in this branch, in the first branch, I get 0.206. In the second branch, I get 0.171. And in the third branch, I get 0.286. Now, Kirchhoff's junction law states that these all come together and they all left with that total current. So if I do 0.206 plus 0.171 plus 0.286, I get a total current of 0.663 amps. And that is my correct answer. That's the current provided by the battery. But there's another way of solving this problem. And I'm going to point that one out right now. The concept of equivalent resistance means I take this complex circuit and I replace it with one resistor. And this is the equivalent resistance. And this is still a 12-volt battery, and the concept is that the current does not change. So what is my equivalent resistance when I have these three resistors? Well, it's the sum of the inverse of the resistors. And I take the inverse of that. So 1 over 58 ohms plus 1 over 70 ohms plus 1 over 42 ohms. And I take the inverse of that, so I put that to the -1 power. And if I do that, I get 18.07 ohms. And finally, if I take my 12 volts divided by 18.07 ohms, because that's current is voltage divided by resistance, that's Ohm's law, I get 12 volts divided by 18.07 ohms, and 12 divided by 18.07, I get 0.664 amps. All right? Well, I had 0.663. I solved it a different way, and I got 0.664. Why is it slightly off? There's a ton of round-off errors in all of this, okay? But we see that in either way that I solve this, I should get the same current. I could either get the equivalent resistance and get the current coming out of the battery, or I could get the current through each branch and add them all together. So there's different ways to analyze the same circuit. All right, here's my quick little math of finding the equivalent resistance, and there's my equivalent resistance, and then plugging it in to figure out the current coming out. But Kirchhoff's junction law is just as good, knowing that each branch gets 12 volts. Just because I look at a problem a different way doesn't change the physics behind it, and that's what I love about physics. All right, so parallel resistors. So a couple quick little things about them. It would seem that more resistors make sense that it would have more resistance. This is absolutely true for resistors in series, but not in parallel. Parallel resistors provide more pathways for the charge to get through, so it can split up. So the equivalent resistance of several resistors in parallel is always going to be less than any single resistor because of these additional pathways to split up. So think about driving in heavy traffic. If there's an alternate route for more cars to travel, more cars can flow through that highway then. And with a series circuit, there's only one path. But with a parallel circuit, you got all these different branches, and that's going to mess up with the flow. That's going to mess with the flow of the current through those branches. So I got a quick check here. I have a 12-volt battery. This is actually similar as before. 12 ohms, 6 ohms. Equivalent resistance is the sum of those two. It's 18 ohms. 12 using Ohm's law, 12 volts divided by 18 ohms, I get 2/3 of an amp. All right, what about this one though? A little bit more confusing. Each branch gets 12 volts. So one way is to say 12 volts divided by 12 ohms, that's going to be 1 amp. The other one's going to say 12 volts divided by 6 ohms, that's going to be 2 amps. And there is, therefore, 3 amps coming out of that battery. Identical resistors set up in different ways changes the current. So with this, the battery has to push off more currents to give each individual branch that full voltage drop. So what's going to be true about this battery? It's going to die faster because it's pushing out more current. If you think about current as the flow of electrons, and a battery is just holding electrons, it's going to be pushing those out faster, so it's not going to last as long. All right, what happens here? So this is actually kind of confusing because the current initially is just a series circuit. So 100% of the current goes to resistor 1, and the voltage drop across resistor 1 is going to equal the voltage drop of the battery. As soon as I close this switch, the current has a branch and it can split. And although I get a second resistor, okay, the equivalent resistance goes down because now I have different paths. I have branches to follow. So if the equivalent resistance goes down, the current is going to go up because now each of them gets that full voltage drop. So there's so many more electrons that have to leave the battery. All right, one last little quick check. What happens to both bulbs are glowing? We're in a series circuit. What happens when the switch is closed? Okay, I get a branch here again, right? No matter what, stuff's going through A. But when I close this branch, this is what's known as a short circuit. I shorted out B, because what's my resistance across this wire? Well, it's 0. There is no resistance. So current's going to split proportionally, which means that if this is the path of least resistance, which is 0 resistance, it's actually going to short out bulb B, which is crazy. If I think of it, though, I could solve for the equivalent resistance, right? Then I get 1 over 0 plus 1 over whatever B is. And that doesn't make any sense because it's shorted out. So my equivalent resistance will actually go down, which means my current will go up. More current going to A, 0 current going to B. A gets brighter, B goes out. All right, so these are some weird things to be thrown at you right away as you're just starting to learn to analyze circuits. But if you can analyze and think about what's going to happen before and after a switch is closed, that's all you really need to understand for this class. Is we're just getting into the basics of these of circuitry. So the only place to go from here now is to actually go through and talk about more about how we solve series and parallel circuits. So we're going to do a lab on series circuits. We're going to do a lab on parallel circuits. We're also going to have a whole nother discussion about analyzing series circuits and analyzing parallel circuits. And we'll be doing that in the next couple sections. But before we get into analyzing that, let's go ahead and make a quick little summary chart to help us make sure we have everything right. So we have series and parallel circuits. In a series circuit, the voltage has to add up. So the voltage of the battery equals the sum of all of the voltage drops. So for example, I'm going to have example circuits down here. Here is a series circuit with 2 light bulbs. The voltage drop, the sum of all the voltage drops has to equal 0. So the voltage of the battery equals the voltage drop across R1 plus the voltage drop across R2. So it's the sum of the voltage drops. The current in a series circuit, there's only one path. The current is the same throughout a series circuit. Okay, the current is the same throughout a series circuit. Resistance. Well, the more resistors I have, the more the resistance of the circuit. So the equivalent resistance in a series circuit is going to be the sum of all the resistors in that circuit. So if I have 100 resistors, I add up all of the resistors, and that gives me my equivalent resistance. All right, now let's think conversely. Let's think about the parallel circuit. So here's my parallel circuit. There's my first light bulb, and there's my second light bulb. Voltage. The voltage drop is the same across each of the branches. So there's R1, there's R2. So the voltage drop, they're both, you can trace paths directly back to the battery in each of those cases. So the voltage drops are the same throughout each of the branches. What about the current? Well, this gets us into junction law. The current splits up. So the current of the battery has to equal whatever goes across the first branch plus whatever goes across the second branch. And I could have 3 branches. Let me draw a third branch. We'll just add that in there for good taste. Well, now the voltage, hey, voltage 3 also gets the full voltage of the battery. And now the current is the sum of all 3 of the currents. The current coming off the battery. What has to happen? The battery has to push off more current. The battery works harder to light all 3 light bulbs because they're all getting the EMF of the battery. What about the resistance? The resistance we already said goes down. And the formula for that is 1 over R1 plus 1 over R2 plus however many I have, 1 over Rn to the -1 power. If these are all 2 ohm resistors, it's 1 over 2 plus 1 over 2 plus 1 over 2. That's 3 halves, right? The equivalent resistance is going to be the inverse of that, and it's going to be 2/3. So it's going to increase the current the more resistors that I have. And that is a quick little summary chart for all of series and parallel circuits. Now, yes, it can get slightly more complex, and then we'll get into the concept with complex circuits. So let me just draw a quick picture of that. So with a complex circuit, here's my battery. Here's a little series, okay? That's a series circuit. A complex circuit just means that I'm going to add a branch. Whoa. And then maybe I add another branch. Whoa. So if I'm looking at the pathway, there's all these different pathways that current can flow. And this is a complex circuit, and we're going to analyze these by drawing what we call equivalent circuits or equivalent resistance circuits to determine our biggest question: what is coming out of this battery, and how does it split into I1, I2, and I3? And we've taken a look at that, and that's our last section in this chapter.